Hello Internet, I am Jeff and this is Introduction to Programming in ATS, Chapter 10, Datatype Refinement. Let's look at this incomplete program here on the right. It has a type, a function over the type, some values of that type, and then presumably you'd have a bunch of other code that's actually useful. Now the function is declared to take a careless right here and return a char. And by the function name you can tell it takes the careless and returns the fifth char of it. Now, careless, of course, they can not have a fifth member. Like nil is a valid careless. Like the type name here again is careless. So nil by itself, that's a careless. This function says it accepts a careless, so it would have to accept nil. And nil obviously doesn't have a fifth member, it doesn't have any members. And of course, bad list here only has two members, doesn't have a fifth member. So, we don't actually define get fifth member here. And this is ATS. It can actually be defined in C. And C is C. We could actually define it with no error checking whatsoever. It just takes what it thinks is a careless, and then it goes through it to get the fifth member, and then returns that. And with no error checking, that'll probably be a segfault. Well, that'll definitely be a segfault if you hand it nil or you hand it a list that's too short. So, if you don't want a segfault, there are some things you can do. And typically in functional programming languages, what you would do is you'd say, okay, this shouldn't return a char. Instead, it can return an option char. So in this case, you have checking within the function, and there's runtime checking now to make sure that you can return a char. And then there's also runtime checking, like when you receive the function, you gotta take an option char and say, okay, is that a none or is it a some char? And you gotta pull the char out and have error handling and so on. Or you could have it still return char, but you could have it throw an exception. So we'd probably call this get fifth member x in that case. So it'd return char but throw an exception when there is no char that it could return. In both cases, you have your runtime checking every single time you call the function. But another thing you could do with no error handling whatsoever is you could just have a human look at your code and confirm that there won't be any errors. It's something you might actually do in a C program or some other low-level language program. You can actually just look at it and be like, yeah, what I'm doing here is dangerous, but it's never actually going to fail, so let's just go with it. It's something people do sometimes. But how can a human actually do that? Why compilers can't do that? Compilers can't do that because, hey, look, this is a char list. This function says it takes a char list, and a char list that if you have a value of type careless, well, this mylist is a char list, and badlist is a char list. So I mean, there's no type error if you pass something that's going to result in a segfault. So the type checker can't help you. But what's the human looking at? Well, the human is looking at other information that doesn't get captured by the type system. Like, hey, this value is definitely it definitely has 5 elements. I can see them. There are 5 elements right there. Or if I have a bunch of code here, I know within that code that somelist has more than 5 elements. So get fifth member is totally fine within here. And I also know that if there's an else here, then you definitely can't call get fifth member on it. So it would be a bad idea to call that function here. Because no, it doesn't have more than 5 elements then. Or it could have exactly 5. So let's make it a little bit simpler and say greater than or equal to. So now it's definitely bad to call it here. So a human reading the code, in order to say whether the code is actually safe or not, is looking at control flow, and it's looking at the actual values at hand to say whether it's good. Now, there's some things that a program couldn't even potentially look into. Like a human will say, "Oh, well, I know this." Let's say you have an HTTP request, and the human knows that the HTTP request always returns a list with more than 5 values. I would think that's a pretty unsafe thing to rely on, but you could actually have a program that never crashes, that totally could crash if that request ever failed. But the point then, the point again is that for the type system, for the compiler, there's no type error because all it knows about a value of type careless is that it's a careless. It doesn't know about nil or cons or any of that. It doesn't know anything else either. It doesn't know again, these are all careless. So what dependent typing does is allow humans to sort of tie information back in. It allows them to give the compilers information they normally don't have. So if you say nil, it creates, let's say this is a careless int event instead. And then you have, well, nil as 0, and then cons is it's an n, is some natural number, or actually it's a positive number. And then you say care, and then careless here, this would be an n minus 1. So if you pass a careless, so if with cons, like over here, like this cons used right here. So this is an invocation of cons. So on the first argument is the character e, and the second argument is nil. So if you pass it e and nil, then you're passing it a char, and you're passing it a careless 0, because that's what nil creates right here. And then this will return a cons 1, so which is exactly what you have. You have an element of one list, so or a list of one element. So yeah, by doing this, now as soon as you refine your data types with information like this, and you don't have to use numbers for length. You could have like an int and encode other information there, and you also have booleans as well, and of course types more famously, but that's something similar. That's a bunch of all languages have that pretty much, except for Go. But the point is, once you do that, then now my list is no longer just a care list. Now it's a care list 5. And bad list is a care list 2. And then some list is a care list n, where n, it might not actually not be defined at all. So get list from file name just doesn't know how big the list that it just finished creating is. That's possible. That's kind of lame, but it's possible. And in the case that you have that, a careless n, well, that means if you call get fifth member from it, let's see, where n is greater than or equal to 5. Okay. If you call careless n where you have no idea what it is, it's just an int, then when you pass somelist to get fifth member, then ATS can no longer prove that this is correct. Like, now there is a type error. It's not just a care list on one hand and a care list on the other hand. It's a care list of some number and on one hand, and then a care list that has a constraint against it. It's greater than or equal to 5 on the other hand. Those are not the same thing, so you can't use them together. But if you do a test against it, like say length somelist is greater than or equal to 5, then ATS could know, oh, okay, that's fine now, and there's a little bit more to be said about like how ATS can infer this. It's not like it magically just knows about length. The length function itself against care list would have to the information would come from the length function. So you'd have something a little bit more complex than these signatures here against it. You probably have to tie the boolean. No, not a boolean. It'd be something like this. Extend on length, and then you have an n that's an int. You take a care list of n, do like this. It takes a care list of n and returns an int of n. So the n is the same in both cases because you repeat it like this. So there's an n here and an n here using the same variable. So not only are you getting the length of the care list, but you're also asserting statically that the number you return is going to be the same as the n that the care list is refined by. So ATS now knows that, and then ATS also knows about comparisons like this. So it says, oh well, the number that somelist returned is greater than or equal to 5, from which you can infer that the care list, the end of the care list is also greater than or equal to 5, which means you can now pass it to get fifth member. So that's cool. So data types are cool, but they're imprecise because you only have careless. Just like if you had a value of type int, val x of type int equals something. But the type system only knows that this is an int. So if you were to say, okay, well, val val with a plus, so it's the plus requires it to be statically known. So 5 equals x. Well, this, even if you have 5 like literally right here, I think that might actually fail. I think you have to like strip it. I think ATS tries a little bit harder there, but it wouldn't do that in the case of a dependent type for sure. Let me see if you did that as well to strip off any int ends. If you did that, so it's definitely 5 and it's definitely int and it's only an int, then this would give you compile time error. It's like, I don't know that x is really 5 there, because it knows that x is an int and it knows that this is an int of 5. All right. So data types are the same thing, the same problem of imprecision that you have with all non-dependent types. And by refining them, you can get more information. And what that gets you is, one thing it gets you is that you don't have to have tests in every single function call. Like gets with member doesn't have to test the length of everything it gets all the time. It doesn't mean there are no tests in your program at all. Like right here, here's a test, and this test turned a careless of n into a careless of greater than or equals 5. So tests, you still have tests in your program. You're still actually testing things to make sure they're good. But now you have the test that you need, or at least you have a program that works with the test you have that's proven to work. So you don't have to have tons of redundant tests. And that can, there's performance benefit there for sure. But also, I mean, that's not really the theme of the book. Isn't here's how you get great performance. It's here's how you can be precise. So you can be more precise by saying, this function doesn't take a careless. It definitely takes a careless of greater than or equal to 5. And then it might be that every single time you call this function, you have a length test in front of it anyway, so you're back where you started. But at least the function itself doesn't have to care. By being precise, it can be a little bit simpler in its construction, for example. I could implement it and say, get fifth member, list equals cons, okay, like this. So cons there. So you can implement it like that. And that'll be fine, probably. All right, so I know this is a little bit odd, but that's actually the chapter. You can go and read it if you want. There's a sequentially and pattern matching that's worth noting, but otherwise it's just talking about pretty much what I talked about here. And I don't think this chapter in particular, I think, is actually very easy to understand, so I don't want to be too redundant in repeating it. All right, that's it.